Hey everybody, welcome to lesson number 3. So this lesson looks at measuring equilibrium concentrations. So how can we do that in lab, and then how can we use those to actually calculate out some important values here. So unfortunately, unlike last lesson, we're not always given the equilibrium concentrations in order for us to calculate K. Sometimes we have to figure out what the concentrations are at equilibrium. We can do that in different ways. So one of the methods that we can use is using a scientific method using a special instrument called a spectrophotometer, and the entire piece there is called spectrophotometry. And so what spectrophotometry is, it's just using particular wavelengths of light to determine the concentrations of reactants or products. So take a look at this equation here. I've got iron 3 in aqueous state, so we've got some iron ions floating around in solution, and they're going to react with some thiocyanate ions to produce iron thiocyanate. Now, iron thiocyanate has a deep red color, whereas the reactants are colorless. So as this reaction goes to completion, the saturation of color is going to start to increase until we reach that equilibrium. And so a spectrophotometer is a special instrument that uses white light, breaks it apart using a prism into different wavelengths of light, and then you can select the wavelength. So this little slit right here can move up and down the electromagnetic spectrum here and pick and choose a particular wavelength of light. And so as it picks that particular wavelength of light, we know how much incident light is actually going to be present there, because we know how much is being given off by the instrument. That's going to be shone through a very special container called a cuvette. Now, cuvettes are really special because they absorb almost no light. And then inside there is where you're going to have this solution going on, where this reaction is taking place. And where this reaction is taking place, that solution is going to get a deeper and deeper in red color. And of course, the more concentrated it is, the more you end up absorbing that particular color of light. So you'll notice that we have an incident light, which is very deep red, and then of course some of that light gets absorbed by the solution, and then we transmit light through that particular cuvette to a detector on the other side. And so the more light that gets absorbed, the more saturated that solution must be, and so the higher the concentration must be. So that's a good example of an instrument or instrumentation that's able to determine the concentration of what it is that we're looking at. So let's look at a practice problem here. Now I know this looks a little daunting here, but it's not actually as difficult as it might seem at first glance. So the question reads, if the initial concentration of the aqueous iron was found to be 0.0064 capital M, so for those of you who aren't familiar with it, capital M is moles per liter or molarity, and the initial concentration of the aqueous thiocyanate ion was 0.0010 molar, and the equilibrium concentration of the iron 3 thiocyanate ion was found to be, by spectrophotometry, 4.5 times 10 to the minus 4 moles per liter. What are the concentrations of the reactants at equilibrium? So it's asking us, what are these concentrations at equilibrium? So there's a lot of language in these questions. You're going to have to dissect them. So the first thing you're going to want to do is write down a balanced chemical equation. You'll notice that in the balanced chemical equation, I have a coefficient of 1 for my iron, 1 for my thiocyanate, and 1 for my iron thiocyanate on the other side. And down the left side of my table that I'm producing here, I'm going to write I, C, and E. Now, I don't usually write out their full words, but I stands for initial, C stands for change, and E stands for equilibrium. These are called ICE tables. And let me tell you, they're going to become your best friends in equilibrium because they help us determine everything. And then I'm going to start populating what I know from the question into the ICE table. Now, whatever you put into this ICE table must be a concentration. So make sure, if it's not capital M, if it's like moles, make sure you convert to moles per liter before you actually put it in there. So I know it says here initial concentration. So remember, the first line in this thing is initial. So initial concentration of the thiocyanate ion and the iron ion are given in the question. So I've written them down here, 0.0064 and 0.0010 moles per liter. Now you'll notice that I've written 0 here for the iron thiocyanate. Well, why is it 0? Well, it's a product. I haven't made any product yet. So initially I don't have any. And that's why I'm able to put a 0 there. And then it says, if I continue reading the question, it says the equilibrium concentration. So now I'm going down to the bottom row here where it says equilibrium. It says the equilibrium concentration for the iron 3 thiocyanate ion was found to be 4.5 times 10 to the minus 4 moles per liter. So that's what I've written down here. That's the equilibrium value for the iron thiocyanate ion here. Great. So when I look at this particular thing, this particular ice table, I notice that there is a middle row called the change. And so I'm interested in the change because the change has to agree with the stoichiometry of the problem. So for every one iron and one thiocyanate that react together, I get one iron thiocyanate. So everything's in a 1-to-1-to-1 ratio here. So when I had 0, I increased by a factor of x to produce 4.5 times 10 to the minus 4. So it's easy to see that my x value is equal to 4.5 times 10 to the minus 4. That's my increase. It went from 0 to 4.5 times 10 to the minus 4. But for every one of these that increases, I decrease by one of these and one of these, same values. So my x's here for the decreasing side are going to be minus x's. So 0.0064 minus x is what we should get for our equilibrium here. 0.0010 minus x is what we get for our equilibrium here. Over here it was 0 plus x, giving us 4.5 times 10 to the minus 4. That's why we know that the x value is 4.5 times 10 to the minus 4. Once you've produced this final line, even with the variables, as long as you know what your x value is, you can determine your other value. So you just take it and actually do the math. So 0.0064 minus 4.5 times 10 to the minus 4 is going to produce 0.0060 molar. That's your iron thiocyanate's concentration at equilibrium. The iron ion. The thiocyanate ion is 0.0010 minus x, which is 0.0010 minus 4.5 times 10 to the minus 4, which produces 0.00055 moles per liter, as you guys can see here. So that answers the question as to what the equilibrium concentrations are. Now, this one still gave you a little bit of information on what the equilibrium concentration was for at least one of our chemicals here. What happens when I don't give you one? And let's look at example number 2 here. So it says here the below reaction happens at 700 degrees Celsius and it has an equilibrium constant of 0.83. It says suppose that you start with 1 mole of carbon monoxide gas and 1 mole of water vapor in a 5-liter flask or container. It says what amount of each product would be present at equilibrium. So here's my balanced chemical equation. I have 1, 1, 1, and 1. Everything's in 1-to-1-to-1 ratios here. But you'll notice in the question I gave you the number of moles of each of these. So you need to convert to moles per liter. So you take the number of moles divided by the volume in 5 liters and you end up with 0.2 moles per liter. So you'll notice that initially I start with some carbon monoxide and some water. I don't start with any hydrogen gas or carbon dioxide gas. So you'll notice that initially remember I is initial, 0.2, 0.2, 0, and 0. In terms of change, I know that I'm going to decrease these ones and increase these ones. Well, how do I know that? 0, you can only go up, which means these ones must be going down. So I must have some reactants turning into products. By how much? Well, by a factor of x. So I'm increasing by a factor of x, I'm increasing by a factor of x. Now, of course, if there was a 2 in front here, let's say there was a 2 in front of this carbon dioxide, then this would increase by a factor of 2x. So you guys will get the idea, and we'll look at some other examples moving forward. So if I know what my initial conditions are, if I add them to my change, I end up with my equilibrium condition. So 0.2 minus x is 0.2 minus x at equilibrium, 0.2 minus x is 0.2 minus x at equilibrium, and then 0 plus x and 0 plus x is just x and x at equilibrium. Well, I've also in this particular case given you the equilibrium constant. It's 0.83 as shown up in the equation here. So if it's 0.83, then I can set up my mass action expression, which is my concentration of my products raised to their coefficients. Everything's a 1 in this case, so I didn't write anything, over the concentration of my reactants raised to their coefficients, as I've written here. Then I can take my equilibrium values and start plugging them in. So I know that the equilibrium value for H2, which is in this column, is x, as I've shown you here. Same thing with CO2, that's also x. And these ones are 0.2 minus x and 0.2 minus x. Now, I can actually simplify this equation by collecting my like terms. So x times x is just x squared. And 0.2 minus x times 0.2 minus x is 0.2 minus x squared. Now this particular example is easy. They do get harder and you may have to use the quadratic formula. We'll go over that in other questions, so don't worry too much about that right now. I can actually take the squares out of this, and so I can simplify it further by doing x over 0.2 minus x to the power of 2. Remember, I just pulled the squares out. And then I can take the square root of both sides. So the square root of this side and the square root of this side would cancel out the square there. And so I end up with 0.911, which is equal to x over 0.2 minus x. I can take this whole denominator and bring it up and then use 0.911 to expand out using FOIL. And then I can take my x's and put them on one side and collect my like terms on the other, and I'm able to determine the value of x. Now, why is that value of x important? Well, if you recall, there's x values here that we are trying to determine. So it says what amount of each substance would be present at equilibrium. So the x's are easy because we just calculated it. So it's 0.095 moles per liter for our x, which is also equal to the concentration of H2 and the concentration of CO2 at equilibrium. The other one, we've got to do a little bit of math. So I take my x value, which was 0.095, and I sub it into here and here to calculate out that their concentrations are 0.105. Now, do these numbers that I got make sense? 0.105 and 0.095. Well, which one's bigger? Well, the 0.105 is bigger than the 0.905, which means that my denominator here is going to be larger than my numerator, which makes sense because the K value we got is less than 1. So remember, the K value tells us where the equilibrium lies, if it's greater than 1 or if it's less than 1. Well, if it's greater than 1, it's going to be product favored. If it's less than 1, it's going to be reactant favored. You'll notice that my reactants have a higher concentration, so it's going to be reactant favored. We're going to have more reactants than we do products in this particular case. If you have any questions with these, send me an email and I'd be happy to help you out.